the recording now. So welcome back. I think today the first thing I want to talk about is I'm trying to re-update the slides very slowly, so I might add more stuff over time. For example, last week I think I show in the textbook by Nelson and Chuang. Okay, sorry about that. I forgot to switch the screen. There is this question about describe a Turing machine to add two binary numbers x and y modulo 2, and then you try to look at the conditions. So your inputs are the numbers from the tape, and then it is in the form of x, and then followed by a single blank, and then y. So you have x, b, y. So this will be your tape. So the thing is, for your tape, you don't really know how long is your x and y. You just know that for your x and y, you need to make them equal in the length. So if one number is not as long as the other, then you may assume that it had been paired with leading zeros to make sure typo the two numbers are the same length. So I try to do the question, I think is here. Yeah, so this would be the question. Actually, it's also quite interesting to try and error because it really helps you to understand how the Turing machine works. And I feel like this should be how the journal club is going forward. Like, I'll probably list down some of the very interesting questions from Nelson and Chuang, and then there will be no answer from the textbook as well. So I might be able to do it. I might not be able to do it. I don't know. But in this case, I just managed to do it, so I just show you how to do it. So essentially, if let's say you have the tape, so the logic is that let's say this is the blank, and then you have like another three numbers. So let's say this is 0, 1, 1, 1, 0, 1. So what you are trying to do is to so let's say this is also blank. So what you are asked to do is to identify whether these two numbers, x and y, when you add them together, they are even or odd. That's what it means, modulo 2. So this is your question. So you need to adjust your Turing machine in such a way that you can evaluate this addition modulo 2. So then the logic behind here is you have to go to the right as fast as possible. Once you reach the blank, you go back in front and then register this value. So when you register this value, it means that you need to change your states because now you are going into a if loop. If you think about it from a programming perspective. So now you are entering if loop. So what you need to do is when it is 0, so this is the first number. Let's say this is A, this is B. So then you sort of like have a if kind of situation. If A is 0, right? So no matter what B is, it will give exactly what B is. So you just copy the value of B, and that's how you end your loop. And then if let's say A is 1, then B also has the possibility of being 0 or 1. So in this case, when B equals to 0, then you have to be applying a NOT, sort of like a NOT gate, so that it becomes 1. Here it becomes 0. So these are two scenarios that you can set your states. So let's say this is state I, then you set another state J. So what you need to do is to, once you read the number of A over here, then you sort of like split into two parts. So you can write if A is 0, then what will happen? If B is 0, then what will happen? So you sort of like set up an if loop, an if condition. So if you look at the answer that I have, basically the first one, you start with the zero state. You start with the zero state. And then at this point, you just need to go to the right as fast as possible. So it doesn't matter what you encounter, you always go to +1. And because you are sure that before you encounter the blank, you won't encounter any other blanks, right? So then what you need to do is to only look at the 0 and 1 state, and then don't change anything, and then keep going to the right. As soon as you encounter B, right, you fix the blank, and then you go back to the left. So this means that as soon as you reach here, you go back one step before. So now you enter the if part. So here I said if it is even, which is 0, then you jump into state 2. If it is odd, which is 1, then you jump into state 3 loop, and then you +1. So the purpose of having S1 in this case is to set up the if condition, and then you just go back to the right. So now in this case, right, over here is 1. So it means that you have to go to state 3. So now let's look at state 3. So basically for state 3, um, here I kind of like trying to set up, because when you, okay, when you are S1 over here, so you jump, you set it to S3, and then you jump here. Okay. So at this point, you need to have a way to go to the right without changing the blank. So that's what I did. For S3, whenever you encounter the blank, you go to another state called S5, and then you keep the blank, and then you go to the right. So now when you encounter this blank, you go here and it becomes X5. So then you keep on reading. So what happens on S5 is over here. So again, you go to the right as fast as possible until you reach to a blank, and then you go back to the left. So this is the function of S5. And then as soon as you reach the blank, you go back here, and then you jump back to S3, because S3 is your evaluation of the odd scenario. So when you jump back to S3, you know that you are going to encounter either 0 or 1. So S6 will be my halting stage. So here I set up S3 in such a way that when you meet with 0, you change it to 1, and then you just stay there. If you meet with 1, then you change to 0 and you stay there. So what it does is that when you go back here, it encounters 1. So I will change it to 0, and then this will be my halting stage, S6. So the Turing machine that you are pointing towards, this number that you have changed will be your final answer. It will be the output that you can read. So the similar strategy can be used for the even version, which is when you encounter a 0 over here. So that's kind of the logic for this particular question. And I think what is even more interesting is that you can try an error. Um, Essentially, you can consider your any states because you have 0, 1, and blank. So you can consider your any states as having a 3-state kind of thing. And then you can see how you can compact your code into like using as little states as possible. Of course, it doesn't really make sense for you to do that because you are assumed to have unlimited states and unlimited length of tapes. But this is something that might interest people to see how to do it. So, and in fact, you can sort of like break down the if loop over here by writing more states like S7, S8, and so on. So that you don't really need. Where is that? So that over here, I think. So because here initially I'm only using S2 and S3 to jump forward with the blank. But for S2 and S3, the 0 and 1 is not being used. So you can either use a new state or you reuse the S2 state in such a way that you can set it to the halting state. So that's what I did over here. And I find this interesting, to be honest. So this is more or less for this particular question. I put it in the previous meeting slides. So now let's go to what we are about to discuss for today. So last week we discussed about the Turing machines, whereby you can think of the Turing machines as the ultimate computational model, whereby every functions or algorithms that you might be able to compute, you can compare it to a Turing machine. So another model of computation that we are familiar with is what we call as the circuit model. So essentially, we know that coming from our experience doing the digitals and computers and whatnots, you know that a circuit basically you consist of wires and logic gates. And a logic gates basically is a function of taking some inputs of 0 and 1 with k inputs, and then it gives you L outputs of 0 and 1. So we don't allow loops. So like for example, if let's say this is your NOT gate, we don't allow something like this to happen so that you don't create some instabilities inside your digital circuits. So some of the very important logic gates, as we know, is AND gate, OR gate, NOT gate. NAND gate is basically an AND with a NOT gate combined, and NOR is a OR gate and a NOT gate combined. But what is not being discussed explicitly is the fan out and the crossover. So basically, for fan out, it means that you can split 1 bit to 2 bits. So this is basically a fan out operation. Crossover means that you can switch the value of 2 bits by interchanging to each other. So why these two are important? Because having these two operations, you can basically create out what we call as a universal logic gates through these 5. So we also assume that you can prepare some ancillary bits without having any resources or like extra costs, so that when you compute your whatever functions that you want to compute, you have extra working space for your computers. And we, from our experience as well, we know that just by having these few logic gates, you can basically compute any functions that you want. The proof is solely by induction. So what you need to do is to start from what we call as a Boolean function, whereby you take in n inputs of 0 and 1, 0 or 1, and then your output is 1 bit. So then you will identify that this kind of Boolean functions, you can only get 4 different combinations. Either you get identity, meaning whatever input you get back 0 or 1, or you get a bit flip. That's when you get such a flip, or you get a constant function. How you're going to compute it is by using an AND gate with an ancilla 0 bit. So the constant function always returns 0, no matter what kind of inputs you have. Another constant function is the one constant function. You just use an OR gate with an ancilla 1 bit, and you always get the value 1. So these are the only 4 possible combination for 1 bit output. So then starting from here, you can start to increase the number of output bits and your input bits. And you just repeatedly use these 4 logics, and you will notice that you can build out, compute any functions within this kind of dimensions. So that's what it means by just having a few logic gates, you can use it to compute any functions that you want. And the way for you to do it is basically just trying to cascade the circuits and logic gates from the above. So you just keep on adding different gates together, and then you get to this function eventually. So there's also the concept of what we call as a complete universal logic set. So this universal logic set, or like universal logic gates, is essentially like a set of logic gates that you can use to create other logic gates. So of course the ones that we are most familiar with is the AND, OR, and NOT gate combined together. And this is what we call as the complete universal logic gates. You can also, just by having AND and NOT, or OR and NOT, they are also universal logic gate sets. But the minimal set, which is like the smallest set of your universal logic gates, is either NAND or NOR gates. So one of the questions from Nelson and Chuang is basically trying to ask you to show that just by having NAND gate, and you assume that you can use whatever wires that you want, ancilla bits that you want, and fan out that you want, you can use it to simulate AND, XOR, and NOT gate. So the answer is actually at the next slide, and you can easily Google it online, how you can use NAND gate to do it. And this is classical gates, right? So one of the things for quantum computing is whether or not we can create all the classical logic gates using quantum computers. And this is actually not true because of 2 things. The first one is when you have non-cloning theorem, whereby it basically tells you that you... So fan out basically... So what is the idea of fan out? So basically you have, let's say this is your information bit, and you can start with some ancilla bits, and after some operations, you would be able to copy your information bit into the same thing. So you're cloning the information. But this kind of process let's say this is your information qubit, and then let's say you start from 0. You cannot actually do that. And this is due to what we call as a no cloning theorem. So then it means that basically for fan out, you cannot be performed as what you would think easy that you can easily replicate in quantum computing. So that's one aspect of it. Another aspect is basically some of the classical logic gates, they are not invertible. And as we know, quantum operations are unitary and hence they are invertible. So then you also need extra steps to actually replicate either AND or XOR gates like this. So we'll look into what kind of the kind of like quantum logic gates later on in the next chapter, I think. So this is the answer that I found online. Basically, you can find it anywhere. Just type how to use your NAND gates to become the universal gate set. So NAND gate basically means, if not mistaken, 0, 1, 1, 1, 0, 1, 1, 1, 0. So it's basically a AND gate plus with a NOT gate. So then I think the sort of like answer is kind of simple. As soon as you can create a NOT gate, which is not that difficult, an AND gate and OR gate, then basically you can sort of like um, repeatedly use these three gates to simulate, like for example, exclusive OR, exclusive NOR, and NOR gate. And then you're done with this. The question just now. So then one of the questions that people ask is, okay, now you have a Turing machine, and then you also introduce what we call as the circuit model. So they represents two different types of model of computations. If you look at Turing machines, for example, you will notice that you always start with a tape, and then you have a state, and then you work around how your you also have a tape head, and then you work around your tape head and your state in such a way that it moves either to the left or to the right, and it computes whatever algorithms that you want to do. Whereas for the circuit model, you can let's say this is a AND gate. You always try to add in more stuff. Like for example, if let's say you have 4 inputs, you you use a different circuit, whereas you have 2 inputs, for example, you use a different circuit. So what it means is that for Turing machine, your number of input, your number of output is always the same, and you work around the model to get the output that you want. Whereas for circuit models, you can always modify your circuit in such a way that it computes the kind of functions that you can compute. So this kind of different types of models of computations is what we call as the uniformity. So for Turing machines, it's a uniform model whereby you always have the same possible input lengths and your computational device is the same. But your circuit model, especially when we are considering like the Boolean circuit, which is the one that we are using in our computers, is not uniform because based on the inputs that you will have different circuits. You build different circuits based on the number of inputs. So then the concept of having a circuit family comes into play, whereby you try to group all these different circuits together to form a circuit family. And this circuit family, they are uniform when they perform the same type of algorithm complexity. So over here, I mentioned that a circuit family is basically a collection of circuits whereby the number of n here represents the number of inputs that you have for a particular circuit. If it is uniform, then basically you can sort of like compare with your Turing machine that there would be some algorithms that you can run on your Turing machine that generates a kind of like description for this particular circuit family. So that's the idea of how you would compare different types of model computations through the idea of algorithm-based complexity. So the next thing is to also look at, for example, how different models of computations would require computational resources and how you would classify them in a way. So one way for you to look at the computational resources that you require is by studying, for instance, if your problem size becomes very large, what will be your asymptotic behavior of a particular function? So you don't really need to worry about like to the seconds how much computational time you need to do that. You just need to study like what is the lower bound of your computational time and what is your upper bound, something like that. So for this particular part, you basically have three different types of notations. So before that, like if you look at one example given by Nelson and Chuang, so let's say you require this number of gates to actually run an algorithm. But if you look at like a very large number of operations, when your problem size is very large, this number actually is larger than the rest. So in a sense, you can consider this as your asymptotic behavior of your particular algorithms. So one of the notations used is what we call as the big O notation, whereby this is the upper bound of the behavior of a function fn, and the upper bound is another function. So what it means is that when you consider like a very large computational or problem size, then this particular function gn will be upper bounding your function that you want to perform. And this is useful when you want to study the worst case behavior of a specific algorithm, which is why we are most often using this when we want to um, compare, like for example, quantum speed up and so on. The second bound is the big omega, which is the lower bound of a particular function. So the lower bound will be given by gn. And if let's say your n is large, so gn will be a lower bound on your fn. So you can think of this as something like that. Oh, sorry. So the first one will be this. The last notation is the big data notation. It indicates that your fn behaves around gn. And one way for you to check is that if your big O and your big omega notations are the same, then your Fn behaves around the same way as Gn. So over here, they provide some examples. If let's say your function is 2n, then your big O notation will be n squared. So you can sort of like see how 2n squared upper bounds the function of 2n. The second one is 2 to the power n, and your lower bound will be n cubed. And you can see how 2 to the power n is upper bounding your n cubed. The last one would be n squared for this particular function. because they will behave more or less the same as 7n squared and 8n squared. Of course, this kind of bound is not a very tight bound. You can, I think part of the research over here is to actually find the tighter bound for particular functions or like a particular algorithms. So this is part of the possible research. I haven't really done these two from Nelson and Chuang, so I suppose we can discuss this next week if you want to. So yeah, this is just like how last week I posed the question on the Turing machine on the addition modulo 2. So you can try to do it at your free time. So we discuss these two next week. So now another so this is a comparison between functions. If let's say you have a particular algorithms, how would you quantify the number of operations that you need to do? Like for example, one way for you to do it is by considering how many for loops you need to go. So let's say you have a compare and swap algorithm. So basically you are trying to compare the letter J and K. If let's say they have, so over here, this is a sorting algorithm. So let's say these two represents two different variables. Maybe you have a list of names that they are not alphabetically sorted. So you are trying to run a function called compare and swap. So for any J and K loops, you just try to compare the two entries. If let's say you set up some conditions, if let's say the first one is A, the second one is B, then you maintain the order. If let's say the first one is C and then the next one is A, then you swap it. So this is the compare and swap algorithm. So one way for you to identify how many, like your algorithm complexity, is by looking at how many for loops that you run. So over here, if j equals to 1, then you run n minus 1 times. J equals to 2, you run n minus 2 times until when j equals to n minus 1, you just run 1 times. So when you sum all this up together, basically you get n multiplied with n minus 1 divided by 2. So then, okay, I forgot to put the bracket. So then you can sort of like estimate the kind of like algorithm complexity that you have, which is around the order of n squared. Because of the asymptotic behavior of this particular function. The last part of this today's, I guess, talk or presentation, I don't know, journal club, is to look at the computational complexity, and this is a really big topic. So I kind of split it into two parts. So previously we talked about algorithm complexity. You can think about how many operations that you run through your computer. You can also think of the time complexity aspect of it, or you can also think about the circuit complexity aspect of it, like how deep is your circuit, how much certain gates that you need to use to run these particular algorithms. Um, of course, there are various types of complexity and they measure different things. So the other type of complexity is what we call as the computational complexity. It tries to study the lower bound of your resources required by the best possible algorithm to solve a problem. Your best possible algorithm might not be known or discovered, but you can theoretically uh, show that there's no way, for example, classical computer would be able to solve this in a certain amount of time, something like that kind of idea. And of course, we would want that the most efficient algorithm to match with this particular lower bound proved theoretically, but this is often not the case. So we might not encounter the most efficient algorithm, to be fair. So that's the difficulty part of this part of research. And usually for computer scientists, they only classify in a very coarse way. Whenever you can compute a certain problem or solve a certain problem by using a polynomial time or space or whatever resources that you need, then you call this P. If it is exponential, then it is called NP. So then basically you can sort of like have two big classes of problems that is easy to solve whenever you can use polynomial resources. Otherwise, it will be hard to solve when you need exponential resources. And the idea of exponential over here is not necessarily means that every time it has to be n to the power of n kind of thing. N to the power of log n is also exponential, but they just kind of like group them together. So these are basically theoretical constructs, and in reality, you might need more operations to complete the algorithm, and more often than not, the most efficient algorithms is not being used because uh, sometimes having more operations they bring you different benefits. So there is another thesis called strong Church-Turing thesis, whereby this thesis basically says that whatever model of computations that you have, uh, whatever kind of algorithms or problems that you try to solve in, for example, if you are using circuit model and you can solve a certain problem, you can always relate it back to a probabilistic Turing machine by having at most a polynomial increase of operations. So again, the strong Church-Turing thesis basically tries to relate back to whatever models that you have to the Turing machine, so that you have one way to compare between the complexity and between the complexity of the problem, so to say. So what is a probabilistic Turing machine? Previously, what we discussed is basically your tape head can move to the left and to the right deterministically. So probabilistic Turing machine basically means that at any step you have some probability to jump to the left or not jumping at all. Or when it is, for example, +1 at the very last step, it has a certain probability to go to the right or not going to the right. So this kind of probabilistic computational model is said to be the strongest possible mode of computations, even though it is stochastic. And the idea of strong Turing thesis actually also relates back to quantum computing because it is a probabilistic model of computations. So what does the strong Turing thesis tries to say is basically, if you cannot solve it even on like this probabilistic Turing machine, right, then that particular problem you have no way to solve it in other computational models by using polynomial resources. So that's the idea of strong Turing thesis. The next part would be to go into the classes of P and NP, which is quite a big topic. So I decided to split it at this point. So I think that's all from my side.